All right, let's do exploration 1 on page 458. And this has 3 parts. And part 1 says, show that a to the x for a greater than 1 grows faster than x squared as x goes to infinity. So if I'm going to show that, that means that in the limit as x goes to infinity, we want to have a to the x over x squared equal to infinity. And I want to know if that's true. And if it is true, then that's going to tell me that a to the x is going to grow faster than x squared. So let's try to evaluate this limit. So I've got my limit. I'm just going to write it again as x goes to infinity of a to the x over x squared. And when I have limits, I usually start by substituting in, and this is going to give me infinity over infinity. But this is an indeterminate form. Fortunately, it's an indeterminate form that I can apply L'Hopital's rule to. So when I apply L'Hopital's rule, that means that I take the derivative of the numerator and put it in the numerator, and I take the derivative of the denominator separately and I put it into the denominator. So the denominator is pretty easy. The derivative of x squared is 2x. The numerator, on the other hand, we need to go back and remember that this is going to be a to the x times the natural log of a. And again, when I substitute in, I'm going to get infinity over infinity, still an indeterminate form, but still something I can apply L'Hopital's rule to. So I'm going to do it one more time. I'm going to have my limit as x goes to infinity. And when I take the derivative of the numerator, I'm still going to have a to the x, but I'm going to pick up another factor of the natural log of a. And the derivative of 2x is going to be 2. So now when I substitute in, I'm going to get infinity, which is exactly what I had hoped to get in the first place. And this tells me that a to the x grows faster than x squared. Okay. Well, let's move on to number 2. And part 2 says, show that 3 to the x grows faster than 2 to the x as x goes to infinity. So again, I want to evaluate this limit as x goes to infinity of 3 to the x over 2 to the x. Now, I want that to be equal to infinity, because if it is, then the function in the numerator, 3x, grows faster than the function in the denominator, 2x. But I want to be a little more creative before I do this. I'm going to recognize that this is the limit as x goes to infinity, but I could take this and make it 3/2 all raised to the x. And now when I substitute in for x, when I let it be equal to infinity, I'm going to have 3/2 to the infinity, which is going to give me infinity, which tells me therefore that 3 to the x grows faster than 2 to the x. And then for the last part, part 3, it's really just kind of generalizing what we did in part 2. And part 3 reads, if a is greater than b is greater than 1, show that a to the x grows faster than b to the x as x goes to infinity. So basically, I'm going to take my limit again as x goes to infinity, and I'm going to have a to the x over b to the x, and I want that to be equal to infinity. And if it is, then I can say that a to the x grows faster than b to the x. Well, I'm going to play the same little algebra trick that I played in part 2. Whoops. I'm going to have the limit as x goes to infinity, and I'm going to make this a over b to the x. Now, I know that a is greater than b and that both of them are greater than 1. And this tells me then that a over b has to be greater than 1. And if a over b is greater than 1, then a over b to the infinity is going to be equal to infinity, which therefore tells me that a to the x grows faster than b to the x if a is bigger than b is bigger than 1.